Mehmet Hoca bugün Zafer Hoca konuşacak herhalde açılışta.
Program. The sixth International Symposium on Sustainable Logistics, held this year, is supported under the TÜBİTAK 2223-B Domestic Scientific Event Organization Support Program. The sixth International Symposium on Sustainable Logistics, held this year, is supported under the TÜBİTAK 2223-B Domestic Scientific Event Organization Support Program. sixth International Symposium on Sustainable Logistics, held this year, is supported under the TÜBİTAK 2223-B Domestic Scientific Event Organization Support Program.
Ladies and gentlemen, I would like to extend a warm welcome to all of you attending the 6th International Symposium on Sustainable Logistics, the Theme of Resilience. This symposium is organized by the Department of International Trade and Logistics at Toros University, Faculty of Economics, Administrative and Social Science, in collaboration with the Turkish Logistics Association, Lazarski University, Birmingham City University, Jean Monnet Excellence on Sustainability, the University of Tokyo, and Foch-Wismar University. We are highly grateful to all parties involved for their contribution to this event. Before we start, here's something special. As you see in the banner, TÜBİTAK, namely the Scientific and Technological Research Council of Turkey, in other words, Turkey's top government-based scientific authority, has chosen to back our symposium. This means this symposium is official recognition under the Domestic Scientific Events Support Program. By the way, together with our friends from Birmingham, we celebrate and congratulate Aston Villa for UEFA Cup victory last night in Istanbul. This symposium has attracted participation from various countries and disciplines, focusing on the theme of resilience. During the event, we will have the opportunity to review almost 50 scientific papers presented in parallel sessions, as well as enlightening the keynote speeches by 3 distinguished speakers. Organized under the main theme of resilience, the main objective of this symposium is to shed light on the latest trends in the fields of logistics and supply chain. It also aims to promote the sharing of current findings and practices, contribute to the advancement of scientific research in these fields, and support sectorial activities. By addressing resilience challenges, we hope to develop common solutions and foster professional and social connections and collaborations among stakeholders. Without further ado, I would like to introduce Professor Demirci, Chair of the Symposium Organizing Committee, to delivering the opening speech.
Thank you. Dear participants, esteemed researchers, and distinguished guests, on behalf of Toros University, I am honored to welcome you to the 6th International Symposium on Sustainable Logistics. We take great pride in organizing the 6th edition of this symposium, and we are delighted to see the growing interest and participation each year, which strengthens the academic and sectoral impact of our event. Till now, we have successfully organized events in collaboration with 8 different partner universities from 6 different countries, and we are very pleased with the increasing interest to this symposium, and it encourages us. For this symposium, again, our partners are Birmingham City University from the United Kingdom, Lazarski University from Poland, Hochschule University from Germany, the University of Tokyo from Japan, and Jean Monnet Center of Excellence on Sustainability from France, and also supported by Turkish Logistics Association and especially the Scientific and Technological Research Council of Turkey. This year, we have chosen sustainable logistics within the framework of resilience as the central theme of our symposium. Resilience in logistics has become a defining priority in an era characterized by geopolitical tension, climate-related disruptions, public health crisis, and increasing supply chain complexity. It refers not only to the capacity of logistics system to absorb shocks and maintain continuity, but also to their ability to adapt, recover, and transform in response to uncertainty. In this sense, resilience is no longer a reactive concept. It is a strategic and systemic capability that underpins sustainability, competitiveness, and long-term operational stability. Strengthening resilience in logistics, therefore, requires integrated approach that combine digitalization, flexibility, risk governance, infrastructure preparedness, and collaborative decision-making across supply chain actors. All these means that the crises are new normal. Throughout the symposium, we will discuss vital topics such as resilience, digitalization, sustainability, risk management, agility, circularity, so on. We believe that this platform will serve as a valuable opportunity to strengthen university-industry collaborations, support young researchers, and expand international scientific networks. I would like to take this opportunity to extend my sincere gratitude to our distinguished keynote speakers, Professor Amir Nejat from Norwegian University of Science and Technology, Professor Peter Helix from University of Antwerp, and Dr. Sui Zonki from University of Tokyo for generously sharing their time, expertise, and insights. Their valuable contributions will undoubtedly enrich our discussions and inspire new perspectives on sustainable logistics. And also, I would like to thank the President of the Turkish Logistics Association, Professor Mehmet Tanyaş, Vice President of the Turkish Logistics Association, Professor Gülçin Büyüközkan, and Board Member of the Turkish Logistics Association, Professor Zafer Acar, who contributed us for this organization and provide all kind of support. I also would like to thank to the Scientific and Technological Research Council of Turkey, who foster us within the scope of domestic scientific event organization support program. In addition, I would also like to express my special thanks to Chairman of Toros University Funding Board of Trustees, Mr. Ali Özveren, Chairman of Toros University Board of Trustees, Mr. Sertaç Özveren, and Rector of Toros University, Professor Ömer Arıöz. And finally, I would like to express my heartfelt gratitude to the organizing committee, whose tireless efforts have made this event possible. Without their dedication and generosity, this symposium would not have achieved its full potential. Let's embrace this unique opportunity to deepen our understanding of different perspectives of resilience and the role of logistics. Welcome again, 6th International Symposium on Sustainable Logistics. Thank you and wish you all a fruitful and memorable symposium.
Thank you, Professor Demirci. Indeed. Now, I would like to give floor Professor Zafer Acar, board member of LODER, to deliver his speech.
Thank you for inviting me. Dear distinguished guests, esteemed academics, respected organizers, and participants joining us from around the world. It's a great pleasure and honor for me to speak again on behalf of the Turkish Logistics Association, LODER, at this important academic gathering, the 6th International Symposium on Sustainable Logistics, this year theme of resilience. First and foremost, I would like to extend our sincere gratitude to Toros University, especially the Faculty of Economics, Administrative and Social Sciences and Department of International Trade and Logistics for hosting this remarkable event. We also wholeheartedly acknowledge the valuable contributions of our international partners, again, Jean Monnet Center of Excellence on Sustainability, Lazarsk University, Birmingham City University, the University of Tokyo, Wismar University, and all others who have supported this symposium, including TÜBİTAK. The fact that this year's symposium is being held in a hybrid format demonstrates our collective commitment to accessibility, inclusivity, and continuity in academic exchange, regardless of geographical constraints. As LODER, a professional association that has long been devoted to advancing logistics education, research, and practice in Turkey, we are proud to support events like this, where scientific rigor meets pressing real-world challenges. Today, more than ever, resilience has become a defining principle for logistics and supply chain systems. In a world characterized by disruptions, whether geopolitical, environmental, technological, or economic, the ability to anticipate, absorb, adapt, and recover is no longer optional. It is essential. The theme of this symposium, as I mentioned, resilience, is both timely and transformative. Over the past few years, global supply chains have been repeatedly tested by unprecedented shocks. These experiences have revealed not only vulnerability, but also opportunities for redesign, Resilience logistics is not simply about returning to previous state after disruption. Now, it is about evolving into stronger, more adaptive, and more sustainable systems. This shift requires us to rethink traditional priorities. Efficiency alone is no longer sufficient. Instead, we must balance efficiency with flexibility, redundancy with optimization, and short-term performance with long-term robustness. In this regard, resilience and sustainability are not competing objectives, but deeply interconnected ones. A truly sustainable logistics system must also be resilient, and a resilient system must be redesigned with sustainability in mind. I believe we are living through a pivotal moment where interdisciplinary collaboration is not just encouraged but essential. Logistics is no longer a purely operational function. It is a strategic capability that shapes how economies respond to uncertainty and change. The diversity of perspectives represented at this symposium is a powerful reminder that resilience cannot be built in isolation. It must be co-created across disciplines, institutions, and borders. From Loder's perspective, we see academia not as a separate sphere from industry, but as its conscience and its compass. Through our support for academic symposia, university curricula, and research collaborations, we aim to ensure that the next generation of logistics professionals is not only skilled, but also adaptive, forward-thinking, and capable of navigating complexity with confidence. Let us also take a moment to appreciate the human element behind this event. Organizing an international symposium, it's no easy task. It requires vision, perseverance, and cooperation. To all members of organizing committee, technical staff, academic reviewers, and contributors, your efforts are deeply appreciated. As we embark on 2 days of rich presentations and dialogues, I encourage all participants to be open, engaged, and generous in your intellectual exchanges. Share your insights, challenge assumptions, and explore new ways of thinking about resilience in logistics systems. To conclude, on behalf of Loder, I wish you a successful and inspiring symposium. May this event not only deepen our understanding of resilience, but also inspire new collaborations and innovative approaches that will shape the future of sustainable logistics. Thank you very much to all of you.
Thank you, Professor Acar. We share all your thoughts. Okay, now we have a little break and then start in 5 minutes with 3 precious keynote speakers. See you in a little while.
TÜBİTAK 2223B Yurt içi bilimsel etkinlik düzenleme
Okay, hi again. In this part of Symposium program, we have the privilege of hosting esteemed keynote speakers who will contribute their valuable insights. Before we proceed with the keynote speeches, let me remind you to hold your question until the end of each presentation. This way we can ensure structure and comprehensive discussion. Now, I would like to give floor Professor Amit Nejat from Norwegian University of Science and Technology to present his speech on AI and digitalization for maritime resilience.
Thank you very much. Good morning, and thank you very much for having me today. Let I start sharing my presentation. Is this in the full screen mode? Is
Yeah, we
clear?
can see. Yes, it's all clear.
It's all clear. Yeah, thank you very much.
welcome.
Good morning again, everyone. My name is Amir Nejad. I am a professor here at Department of Marine Technology, Norwegian University of Science and Technology. Today, I would like to talk about the digitalization and the role of digitalization in maritime. A bit about what I will talk about in this presentation today. Just at 1 minute, I move this toolbar. All right. I will talk about why digitalization and where are we today, especially in terms of digitalization in maritime. How digitalization helping the maritime resilience. I will mainly see this as a perspective of a ship. So the focus will be the effect of the ship, especially on the resilience in maritime. And then some challenges and then some concluding remarks. So I will try to cover these points mainly today in the my presentation. Then we come to why digitalization. Well, if you look to the EU has 6 political priorities, and very interesting that actually one of them is digitalization. So a Europe fit for the digital age is one of the European Commission's 6 political priorities. Why? What is the purpose? It aims to contribute to economic growth, boosting job competition, investment, and innovation in the EU. Well, then what EU basically mean by a Europe fit for the digital age? Let's a little go deeper. These are the EU targets for 2030. So EU, the target is to have the skill, at least 80% of the people to have digital skill infrastructure. But let's a little for us today, look to this part, to the business. So EU target by 2030 is that cloud computing, big data, AI, artificial intelligence, should be used by at least 3 out of 4 companies. I mean 75%. And then for SME, small, medium enterprises, they are targeting 90% to be digitalized. Well, quite ambitious, 75% and 90%. Let's look a bit maybe more local. This is a document from Norway, from what is called National Digitalization Strategy till 2030 from the ministry. Let's look what are the local plan in Norway. When we look to Norwegian document, it's very interesting that they have highlighted a few industry which are digitalization more important. And interesting thing is one of the maritime industry. And obviously for Norway being a marine nation, that is a big industry, as plus 80% of our export is somehow related with marine. And that's why you will see in this digitalization strategy, maritime is very much highlighted. And you will find in this document is open access. If you Google it, you will find a number of places that actually clearly mention maritime industry as one of the focus industry for digitalization. Well, this is also a figure taken from there, like data from the aquaculture, from fishing, goes to the cloud, and then you monitor the fish farm. And there's something which is today even actually is done in Norway. Uh, then what is digitalization? Is it old wine in new bottles? Is it emperor new clothes? These are some interesting things by some colleague in Sweden. They were talking, what is digitalization? If digitalization is the solution, then what is the problem? So is it a new buzzword? What we exactly mean by digitalization? Let's a bit try to understand what we mean by digitalization in maritime in simple word. Let's make the things simple to have a common understanding from the beginning. In simple word, what we mean by digitalization. Very simple, we can say use of data. So if we make it in a very simple word, we can define the digitalization basically the use of data. And for example, for decision support. If you go back to the strategy from the Norwegian government, you can clearly see that saying strong industries such as healthcare, energy, aquaculture, and other maritime industry poses significant amount of data. So the key word is data, and then we talk about digitalization, how we use the data. And that's basically the whole business is about it. I use another word here, decision support. We will talk also about that. But let's see in terms of maritime, when we talk about data, as you know, if we have a ship goes from A to B, we have navigation data, a lot of environmental data, wave, ship data, fuel, performance, speed, failure. And then when we talk about digitalization, how basically we take best of this data for decision support. For example, improving the efficiency, for better reliability, higher reliability, cost reduction, for reducing the failure, improving the reliability again, for better economy and safety. So somehow we use those data for achieving one of these objectives. And in my presentation today, I will give 3 examples of the project we have been done in my group using data for some of these. Uh, Before that, before going to the example, let's have a look to the status. Where we are today in terms of digitalization in Europe. What is the status in how we have progressed over the year, and what is the status today? If we go further, this is published by European Commission. So they have, I think, 5 or 7 skills which we consider digital skill in Europe. And then they did a statistic all around the European country. So the average EU digital skill is about 55% of the people EU consider they are having digital skill. You can see some country lower, some maybe higher. But and as I remember correctly, one of the skill was, for example, using AI, or one was using, for example, search engine. Some of them are simple, some a bit more advanced, but in average, the EU is about 55%. If you go further, another interesting statistic, the use of AI by businesses in Europe, in EU especially. So EU countries, and then also Norway as an associated country. So in average, 12% of the businesses in EU, they basically use AI in their business. Well, not so much, and this statistic is relatively new. So it's not, it is going on. You can see in Nordic country, maybe a bit higher, Belgium, so the Finland, Sweden, Denmark, and Norway maybe a bit higher, and then goes Belgium, Netherlands. But in average, it's not so high, it's about 12%. Well, as I said, let's go a bit deeper and look to three examples. We have been using data, so use of data for getting a decision for either the ship, either for the route. This example that I start with one example, which we work with one Norwegian company here in Norway. We had 5 identical vessels. We had data from them. I will show shortly which kind of data we had. And we have about 1 year data. Then we try to see how we can use those data to develop a tool for predicting fuel consumption. So my students, so he did his work on this project. These 5 ships, the first data we had was the route. So you can see when the area which are red, so they had more port activities. So a lot of activities was done this part of the world between the Japan, Korea, and going to the Australia. So a lot of time over 1 year, the ships they were in those areas. But you can see also like in US, in South America, and even also in Europe. So the ships, more or less, they were going all around the world, but with main activity here. So it was quite very interesting set of data in terms of geographically was covering most of the world. Also, the type of the ships, they were identical. We have quite big amount of data. Okay, then let's how we use it. We start looking what are the data do we have. So we had the vessel name, destination, how long they were on the way, a lot of things about their performance, fuel consumption, some of the things based on the data we had, we could estimate like how are the forces in terms of wind, wave. So we use this data, okay, very interesting set of data. And then we try to develop model. So we use a partial part of the data for training the model, a partial for validation. And as we did, as we were going to the selecting which model is the best, we were minimizing the error. So predicted value from the model, the measure, for example, fuel consumption, is this model giving me the lowest error? Yes, no, then optimize till we come up with the model which we were getting the best response. So this is a model we developed. So you can see this is a predicted response, which was a predicted fuel consumption. And this was the measured fuel consumption, very much correlated. So with very good accuracy, we came with a very good model, which the company used it for estimating or predicting future fuel consumption. For example, for new route planning, customization, for fuel saving. So we use the data, develop a tool which use for better route planning in the company and estimation of the fuel for the future route planning. And that was very interesting use of the data in this case. Let I go to the second one. The second one, what we did again was another company here and another student in my group. We had this time it was a floating LNG, so they're huge, more or less factory, and they have a lot of machinery. So if there is something happen, they damage or failure, they will have a significant effect also for the cities which they are providing LNG or for the port. Therefore, monitoring their machinery is extremely important. We should always have in advance if something going wrong. And again, we have data, so we have temperature, pressure, speed, so there are the measurement data from the machinery on this vessel. And then we try to see how we can again use of this data for understanding something going wrong in advance before something can happen. So again, we developed the model, a data-driven model. This time we try to see, for example, here on the horizontal axis was the consumption, fuel consumption or the power, and then temperature. They were highly correlated, so we could build a function based on the power and temperature, and we trained it with a lot of data we had from the machinery on board. And then one interesting thing, as in this project, we find out is the data quality. So, and then developing a filtering strategy to get high quality data. So you can see here, we had a lot of data, red or yellow, I'm showing here, which we got from measurement, but some of them physically, they had no meaning. Some of them, they were error. So we sit together, and we also invited some expert on the compressor or on those machinery, talking with them. Well, this data, does it make sense? Yes, no. So we develop. So it is very interesting that in this kind of data or digitalization approach or AI approach, we need to have expert knowledge as well in terms of understanding what the data mean. So in the beginning, we had quite a big challenge to have the data cleaning, to have the clean data before we build the model. And that was the first part we did. So we clean the data and then we build the model. Here I'm showing some of the prediction of the model. So the blue one is the real and the red one our measurement. In the beginning, you can see some error, but then gradually we update our model and update to make the model more accurate. And so was the process to model updating, get the model which is as accurate as possible. And what we use it, again, the company uses this. Here I'm showing a case that they have the fault. So here was the fault that really happened, and these are the alarm. And then our model was predicting that as well. So this was for the case that happened, and we saw the model working correctly. So then they use this tool for predicting for the future fault can happen in critical machinery. Again, the use of data for decision support, and in this case, for predicting what can happen in the ship. The last example, this was again was one European project we did, and here what we did is that we developed a digital twin for monitoring the propulsion system on the icebreaker. Why we took icebreaker? It can be applied in any ship, but this icebreaker is especially because we could first instrument it, so we had access to good instrumentation. We had a lot of measurement from them, and also they operate in extremely harsh condition. Therefore, it's extremely interesting case study. But why we did that? Yes, please. Should we take the question now, Mr. Chair, or we should take at the end?
No question, I think. There's no
Something. Do you
No,
hear
we
me?
can hear you.
Okay, okay. Something happened because something stopped my presentation suddenly. Maybe I share again.
Yeah, please.
Because I can hear myself a bit strange. Let I share again. I think something happened to the internet.
Oh, it has come back.
Yes. Is it now full screen? Is it visible?
Yes, yes, it's visible.
Yeah, sorry for interruption. Some problem maybe with the internet. Let's looks to why we do this. Why we are looking to digital twin.
Professor Nejat, can you hear me?
Hello, hello. Yes, I can hear you. But you are a bit frozen.
You too, yeah. Probably there's a problem in the line.
Yes, yes. I think there's a problem in the line because it's interrupting again. Let I share again.
Yeah, it's okay. Now we can see it again.
Yes, yes. Let I share again. Yes. So we look to why we do this machinery, because the machinery, about 40% of the ship's incident, 40% come from the machinery. And they contribute quite a lot on the breakdown of the ship. Therefore, focusing on the machinery system monitoring is extremely important. On the right side, I'm showing, you see this the propeller hit the ice, and then on top, this is a ship in Norway which had the blackout of the engine. And then you see the helicopter is basically saving the people from the ship. Then what we did, we used the digital twin. And then what is digital twin? Digital twin is basically the virtual representative of the physical asset. So basically, we try to mimic the behavior in the model, and the model we are using is either physics-based database or hybrid modeling. So here I'm showing that basically the basic idea of the digital twin. We have physical asset. Let me use this laser. We have physical asset measurement, and then the model, and then decision support back to the model. The measurement we use in this particular ship, we instrumented the whole propulsion system. We put the sensor in different location. In this case, these are measuring the acceleration, so we could monitor what's going on in the system. We then develop different models, model for the propeller, for the ice, if it's hitting the propeller, then understanding what is the load spectrum, what is the load on the propeller, and then we model the motor, we model the whole system of the shaft. So we have model of the whole system in different environmental and different condition, especially if the ship was hitting any ice, we could then see what is the impact on the system. So we have the measurement, we have the model, and then let's use the data we get from this system for decision support. What we did then we developed a tool which we could monitor the ship critical component, propeller, shaft, bearing, electrical motor. So basically, we developed a tool which can improve safety and reliability of the ship in operation, and especially this kind of ship which are going to extremely harsh environmental condition. Then we come to see what are the value of the digital twin. The first important value is that it is capable of predicting the ship behavior based on limited measurement. So we had very limited measurement, but still we could predict what's going on in long term. Then we have what we call virtual sensor. We can predict the parameter which we don't measure on those locations. We don't measure, we call it a virtual sensor. And also we can predict the ship behavior for future condition. Uh, Basically, if we look at the use of the digital twin, we look to historically, if we look to about 100 years or early 20th century, a lot of machinery, they were built to run to fail. But later on, the preventive maintenance came in picture, how to prevent them. But nowadays, we are more on predictive maintenance, where the digital twin can help a lot in terms of predicting the future, what can happen. And that is exactly the importance of the digitalization, use of data for predicting the potential maybe fuel saving, damage. So basically this comes what we call predicting or predictive maintenance. Some concluding remark: we said digital twin in the simple word, use of data, and then we show 3 examples of how to use the data. For example, in the first example was ball carrier. We use the data for fuel saving, and then we use for improving the reliability in the LNG, and then in the last one, the use of the digital twin. How well we went through this process, but let's see that there are challenges. I mean, digitalization doesn't come without challenges. The first challenge is data quality. If the quality of data is not appropriate, not good, normally we will have problem to develop good models. The second comes model accuracy, model uncertainty. And the third one, the ownership, the data, who own the data, who own the model. So the ships as ship owner, the machinery comes from the machinery. So there are their own challenges, and especially if you look at marine specific, then ship sensors, the computers, cloud, who own them, and then access to them. So there are challenges. And then system usually is made by different manufacturer. They have their own component, their own system. They may not let you use the data. The example I gave, we had access because the owner was willing, we use the data, and that was a win-win scenario. But these are the challenges which we normally have in use of the data. And of course, the risk or cybersecurity. And then if you look how affecting the resilience, we gave examples of improving efficiency, higher reliability, cost reduction, reducing failure, economy, improving safety, and all these aspects, if you look closely in, because I mainly now look on the ship perspective, but they have positive impact on maritime resilience. Well, the ship performing better, we have better economy, reducing the cost, all as a system, they are affecting positively to improve the maritime logistic and improving its resilience. And by this, I would like to تشكر and thanks everyone. And sorry for the technical problem. Suddenly my presentation stopped and started repeating my voice again and again. So I had to stop it. So thank you again.
Thank you, Professor Nejat, for your valuable support and collaboration. We all heard it was a great, great speech. So don't bother it. Okay, if it's okay for you, I would like to open the floor for questions.
Perfect. I hope I was in time.
Yeah, you're in time. Perfect time. Okay, if anyone has any question or would like to share their thoughts on Professor Nejat's presentation, please feel free to do so. Any questions?
Okay,
Or any...
I have a question to Amir. Thank you very much, Amir, for this kind of support and this inspiring presentation today. So actually, I'm wondering about your perspective about how can data-driven system contribute to real-time management, risk management, especially in maritime. How can we contribute and how can we integrate this kind of operations in real-time risk management?
Thank you very much for the question. When we look to real-time, for example, logistic and risk management, then we are extremely on the higher system level. So my presentation is on one element ship, which is in the perspective of the logistic management is just one small block, isn't it? But then when you talk about the logistic risk management, then you have port. So in my opinion, that's why I was thinking today give presentation on this element, because you are looking logistic as much higher perspective, but at the end the risk is all this element together. And then in my opinion, it's very interesting that we sit together, we come with what the machinery system ship as one element can reduce the risk. Then you come with the logistic port, maybe the route planning, maybe so then you come another element. Then, other colleagues talk about, for example, now issues with this maybe security. So you see already 3, 4, 5 things we put together. Then we see this as a system level risk assessment or system level reliability. It's very complex, in my opinion. But the best way to do is that we see it as a system of a lot of small elements. And then we can maybe make maybe a digital twin, maybe a virtual model out of it to understand and to assess the risk. It's a very complex system, in my opinion, because it involves engineering, it involves maybe environment, it involves politics, and each of them, they have very different modeling. But I think the best solution is that we collaborate together. There's no other way.
Okay, thank you so much. I think it's need to more different operations can be integrate each other systematically, doing the best solution for real-time risk management.
Totally agree. It's extremely multidisciplinary.
Thank you.
You're welcome. Thank you very much.
Okay. More questions from our guests for Professor Nejat's presentation or thoughts? Okay. Then thank you, Professor Nejat, again.
Thank you very much. And sorry again for the technical issues.
Now, I would like to give floor Professor Peter Hellings from the University of Antwerp to deliver his speech, Data-Driven AI Control in Resilient Logistics.
Thank you for the introduction. I'll try to share my screen.
Okay.
Let me see. You can't see it yet, I suppose.
No, we haven't seen yet.
Can you see it now?
Yes, 100% clear.
Okay, perfectly. If there's anything goes wrong, just interrupt me. That's no problem at all. Okay, let's start. Let's start with the beginning. Who am I? I'm a professor at the University of Antwerp. My focus is on AI. I'm also the head of the department Electronics ICT, and the main focus of my research is on sustainable AI systems in multiple domains. What makes me a bit of an atypical professor is the fact that I already co-founded a couple of spin-off companies. So my research is always very close to industry, very close to the application domain. When you look at my team, we have two big parts in the team. We have a team that is working on sustainable decision making, and we have a team that is working on climate change. Both topics really focused on AI technologies. And when we talk about the decision support and control, there we have the decision support part, which we do in mobility, logistics, construction, and so on. The control part, which is a bit more advanced, and what I will be talking about today as well, is really focused on HVAC, facility management, renewables, and so on. And in climate change, which is another track supported by another professor here, we really focus on weather prediction models using AI and climate change models using AI, and then the effects that climate change has and the effects on the environment and how we can cope with that. In total, we are around 15 people with more or less 10 PhD students and a couple of more senior people. Where are we? I made a map here. Currently, we are all digitally in Turkey, I suppose. But Belgium is up there, and we are totally in the north of Belgium. And why do I say this? When I zoom in a bit, what is our unique selling proposition we have in Antwerp as a university? We are located in this city, and it's a rather small city. And what is the opportunity of a small city? That you can easily build a living lab on that. So we have our living lab in our small city, and it's small but very special. Small, but we have like more nationalities in Antwerp than they have in New York, for example. So it's very representative, but small. So you can walk from the one side to the other side in 15 minutes, which makes it an easy to access living lab. But even more important is when you zoom out a bit. When you zoom out a bit, you get this picture. And then, of course, this particular area is something that interests me a lot. We have a very big port. We have the second biggest port in Europe, which we also try to use as a living lab where we can test the technologies we are building together with, a very big ecosystem. As you saw in the previous speech, Professor Nejat, thank you for that. You see that in AI, Belgium is one of the front runners. We do a lot of that in maritime things, and this is one of the reasons, because it's that important for our government. The legislations allows a lot in this area. And I'm going to show you a small video. I hope this comes through very well. That shows what our port, for example, does, and it will become more important later on. Can you hear the sound?
Hello, I'm Apika. your virtual assistant monitoring all activities in the port of Antwerp Bruges and providing real-time information on weather conditions, air quality, shipping traffic, bridges and locks.
Oh, okay.
Thanks to a digital network of drones, cameras and sensors inspired by the 5 human senses, I can tell what is happening in the port 24/7. In case of an incident, I react and send an alert to a safety officer. When an iNose detects a harmful smell, they can examine the cause and intervene if needed. Autonomous drones and patrol vessels are always on standby to take a closer look at the situation. I help to make activities more efficient and precise. Is a barge berthed correctly and connected to shore power? How much energy are our wind turbines producing? And are all lifebuoys hanging in their closets? Soon, I will even be able to predict the future. By combining historic data and artificial intelligence, I can detect potential congestion and dangerous situations before they occur, enabling safe, smooth and sustainable traffic in the port. In this way, I'm helping Port of Antwerp Bruges become the port of the future.
And this is very important for us, having these kind of technologies on board. And you will see later on why it is important in the rest of my speech. But when you look at Belgium and Europe in general, I think when it's about sustainable logistics, the focus is really on emissions and resilience. And for that, I want to focus today on inland shipping, because I think inland shipping will be a very important player to make that happen. And in that sense, electrification will be a must-have, which is, maybe not as easy as we all think, because, having enough energy in batteries or other energy carriers will be difficult. And then the model shift is essential to do so. But what we see currently, and we are very open in that, is that we fail there. We are talking about the model shift and inland shipping like for 20, 30 years now, and there will be less cargo on the highways and it will be in the water and so on. But it simply doesn't work. It doesn't happen. And what is the main reason for that? I think there are a couple of reasons why those things are not happening. And first of all, there is climate change. And maybe for a lot of you, it's still far away. But when we see, for example, in Europe, we look at the River Rhine, we see that in summer, there are real problems. The upper part of the Rhine isn't accessible anymore because the water is very low. A second thing that we particularly have in Belgium is that there are a lack of captains. When you see the amount of captains that graduates in Belgium every year on an inland ship, it's around 10, and we need a lot more. Then, of course, the electrification is difficult because, you need new infrastructure, you need carriers and so on. And then getting that thing on the water, getting the cargo on the water is not straightforward. And we strongly believe that if we can go for more autonomous inland shipping, that a lot of those problems can be tackled. Main reason for that, there are a couple of important reasons for that. And first reason is we can get the captains off board. We are not saying that we don't need captains anymore, not at all, but we can put them at the shore and we can let them control multiple ships, because a lot of them, the actions can be taken by autonomous AI agents, and the rest, the more difficult parts, can be covered by them. And that will already solve the lack of captains that we have. We will also be more flexible in vessel types, because one of the main reasons that a captain on board is also a problem is because it's the highest cost on an inland ship on the long term. If we reduce cost, we can go for smaller ships, we can go for adapted ships adapted for rivers with not a lot of water, smaller ones, and so on. So that will solve that problem as well. Autonomous shipping will also make sure that those smaller ships, which have a cost, of course, which is compared to the largest ships bigger, we can let them operate 24/7. More optimal operation is essential there. And then, of course, there will be a bigger efficiency. It will be easier to adapt each individual ship towards what's actually needed at that moment in time. So for that, we strongly believe that we need autonomous shipping. And then when you look at autonomous shipping, what you need to solve is this problem. You have a ship on the water, and the ship needs a global plan, and it needs to follow that plan till a certain moment. And when we then dive deeper into technology, what we need to train an AI agent that can do that for us, like a virtual captain. But to do so, we need to know the ship, we need to know the environment, and we need a lot of data. And for that, we need digital twins. Again, thank you, Professor Nejat, for introducing digital twins. I will dive a bit deeper into that because what is a digital twin? The cool thing is that it's new technology. The difficult thing is that everybody has a different interpretation on what it actually is. So let me say what it is for me, and at least then we know what it means for me. Currently, and the way I think you also explained it, Professor Nejat, is this. We have like a physical system. Here it's the cube on the left side, if you can see this. And there are sensors, and it's connected to a model or digital representation. And based on that digital representation, we can, for example, see what goes wrong and what you saw in the previous presentation. And then you can do some decision making, take actions, go for predictive, proactive maintenance even, and so on. And that's what happens. I want to go a step further in this, and that's where it's important for the rest of this speech is we also have that connection. So we have sensors, we connect it to a digital representation, but what we want to do is we want this digital representation to have a control strategy on top of that, which can use actuators to again act on that cube. Let's say that it's a dice based on our hand feels where the dice is. We want to throw the dice a bit differently. That's how we see such a digital twin. And what does that mean? It means that we need three models, three as accurate as possible models. And I explain it with this picture. And you look at this picture, the first thing you see is the environment. If we want to steer a ship very accurate, the environment is the most difficult part. How deep is the water? What is the current? What is the wind? And so on. On top of that, we need a very good model of the plant. We call it a plant model. In this case, it means a model of the ship we want to control. And then what we want to create, of course, is that specific control model. But to do so, we need to have those two other models. So what you see here is we have a plant model, we have an environment model, and what we need to do to make those ships autonomous is we need to generate a control model based on that. And how does it control then the ship? It uses a methodology that we call reinforcement learning, or that's the methodology that we will use in the future. And what it actually does is you are in a certain state. That's what you see here. A state is a description of your environment, a description of the plant, the ship itself. We make a representation, a digital representation of that. And then we predict for each possible action that we can take what the potential reward towards the future is. How well are we doing? And with that prediction, we just take the best possible action out of that prediction. We take the action and we get to a new state. And that's how it works. Of course, the clue is here, right? We need to have like a model that says, given a certain state, a representation of a state, give me or predict to me what the rewards of each possible action is. And to do so, we need that top part here, we need to train. And the clue, the issue is that training such a model and building such a model has two big problems. One problem is what we already heard, data. The second problem is computational complexity. And the computational complexity is easily explained. If you make a problem linearly more complex, the model simulating it will probably have an exponential growth in computational complexity when it's about AI. So we need to tackle both. And the data issue we will tackle as follows. There are three ways to get data. You have the real-time data, which is you are on the ship does something, and you measure it, and you can do something with that. Big problem is it's very, very expensive. And what I often say is if you want to steer a ship based on what the ship actually measures, then it probably takes you the time until the ship has to be taken out of service. So it won't work. Then you, of course, have geospatial data. What do I mean with that? There are a lot of ships on the water, so we can learn from the other ships. But the most important part for me is simulation, where we can let a ship train and learn how to behave in a simulation environment. And as you see, real time, expensive, geospatial, scarce, but the simulation also has an issue. It copes with problems in accuracy. They call it the sim to real gap, the gap between what is realistic and what does our simulation say. So our opinion is we need to combine both. Typically, we start with simulation, we train a lot, then we go to the a bit more expensive data, we adapt it more, and then during lifetime, we'll adapt the behavior or the control models based on what you measure, because a ship is not just in one state. There is a kind of degradation over time. Things change in the ship, so you will need to take that into account as well. And then there is the complexity issue. We need to build a control model with a certain complexity. And there we can take three different approaches to solve that. We can split the problem, which I will explain. We can only simulate what we actually need for a certain decision. And we can take a multi-agent approach. And let us start with splitting the problem. You saw this picture already. And as I told you, when you have a problem and you make it linearly more complex, the complexity will rise exponentially. For that, in inland shipping, we split the problem in three parts. We have a global path planning, which says we are in A, we need to go to B. What would the global optimal path be, regardless of what is at real time happening at that specific location, just taking the geography and so on into account. Then the second part is the local path planning. So we have a global path, and then locally we will do the detection of the obstacles, and then we will adapt locally our path towards avoiding the obstacles. And then the last part is really steering the ship. How do we go from a path towards actually steering the actuators? Then the complexity issue, how do we cover that in simulation? We use different kind of models. When you want to train a ship on how to behave, in the beginning, it's just about finding where to go next. And there, for that, you can use very simple models with very low computational complexity. When you want the ship to cope with current, wind, and so on, you have to go to very accurate, very complex models. We will use these ones first, and in the end, we will add these ones to get to the more in detailed answers to the question. And then, of course, we build intermediate surrogate models. What we do there is we use AI techniques to, based on these models, extract what is specifically needed to learn specific actions, and we will put it in a separate low complexity or lower complexity models. And then the last part is multi-agent, and what you see here in the movie below, it's the spot robots of Boston Dynamics. Instead of training a ship in a simulation environment, we will train a lot of ships in parallel in a simulation environment, and they will learn from each other, and that will speed up things a lot. And how well are we doing at the moment? When you look at our current technology, then you will see, and these are a couple of examples where you see that our ships define the global pathway in an easy way. That's the easier part. But the local collision avoidance, integrating the coloric rules, works pretty fine. And then when we look at the numbers that we get, and when we train just with the middle model, the surrogate model, then we see that we have like a mean track error of 1 meter, but still a not so good maximum track error of 12 meters. and a reduced number of rudder changes, which is important for sustainability. But when we then add our full simulation model as well in the end, then we get to numbers that are fine, that are actually more or less as good as what our captains do. And when you look then at in simulation how it goes, and here you see our local simulator on the River Scheldt in Antwerp. Here you see on the left the power plant. Then we see that our ship in simulation behaves very well and follows all the things that it needs to follow to get to its final destination. But there is more. We built autonomous ship on this. Those technologies are more or less working already. We are now translating it to the real ships. But in another project, which is the AM Paris project, we try to use the same kind of technologies, but then purely on energy consumption. So what we do is we have an input, which is the current energy consumption, a bit what you spoke about, Professor Nejad, as well, in how to predict what the energy consumption is. Here we want to go further. We want to look at the different sources of energy consumption, which is, of course, the propulsion and so on, but also heating, the cargo, also the hotel in the ship and so on. We take everything together, and then we want to build an onboard energy infrastructure that can translate that towards energy demand reductions at certain moments, reducing the peaks, emission reductions, and so on. And how do we do that? Again, we built our high fidelity digital twin, which you see here on the left, where we will put an adaptive AMS system on top of that. And this will use that reinforcement learning strategy again. It will learn from that digital twin and build an approach in how to spend the energy on top of that, given the situation it is in. And of course, it is within a bigger project where you also see that sensing what is actually happening, what the output is very important. So there is a lot of sensor on top of that. And then there is the interaction of the captains, of course. You can't steer a ship itself yet, certainly not the bigger ships. And for that, we need an interaction with the captain. And we have a man in the middle approach in that sense. And when you look at this, we are now building the technology which we will deploy in inland waters, but also at coastal shipping and in deep sea shipping. And we will do this with 10 partners in the entire maritime value chain, as you can see here, which are some of the bigger players in the area. And then last but not least, I'm going to show you even one more small video that also shows that the autonomous shipping, we are not doing that just for the shipping itself, but it's also in a bigger context. All of our work is in bigger projects covering the entire set from sensing till the actual actuation. And here you can see the dealership projects where we are finalizing our results at the moment. Okay, so you saw the movie of the project and how everything was integrated. Now I'm at the end of my speech, I think. So what do you or should you remember of today? A resilient future in logistics needs to include inland shipping, that's for sure. And it will strongly depend on how fast and how well we can cope with autonomous shipping, which will depend on very strong digital twins. And remember, the digital twins, it's a concept that exists already for a long time. It depends on a plant model, an environment model, and a control model, which is connected to our sensors. And there is more that you can optimize. It's not only just the control, but it's the energy consumption, it's the emissions, and it's also the revenue that you can have at the end. And here, I want to thank everybody to have the opportunity to present the work we had. And if there are any questions, please let me know.
Thank you, Professor. Thank you, Professor Hellings. Any thoughts or question for Professor Hellings? I think we don't have. Okay, then. Thank you again, Professor Hellings, for your speech. Thank you for your collaboration and support. Thank you very much again. Okay, now we have Dr. Suiz Zonki. Excuse me. Hi. Now we have Dr. Suiz Zonki, University of Tokyo, to present his speech, Intelligent Maritime Supervision for Safety and Sustainability, Complexity Evaluation based on CGM and MR-XG boosts.
Thank you very much. Can you hear me?
Yes, we can hear you.
Can you see my screen?
Not yet. Yeah. We have just seen.
Okay. Good morning, everyone. It's an absolute honor to be here today to present our team's research.
This honor belongs to us.
My name is Sui Zhongyi. I get my PhD from China Wuhan University of Technology, and after that, I have been working in Hong Kong Polytechnic University as a postdoctoral researcher for 2 years. And now I'm a project researcher in the University of Tokyo. Today, the title of my presentation today is Intelligent Maritime Supervision for Safety and Sustainability Traffic Complexity Evaluation based on CGAN and MR and XG boost. Today we will explore how advanced machine learning algorithm can be leveraged to enhance the efficiency and the safety of intelligent maritime supervision. To begin with, let us look at the macro background behind this research. With the deepening of the global economic integration, global maritime trade volume surpassed 12 billion tons by 2025. However, behind this prosperity lies a significant safety concern. Over 3,000 maritime incidents occur globally each year. Faced with such massive and dense dynamic traffic flow, traditional manual and rule-based supervision has reached its cognitive and operational limits. So why has accurate evaluation of traffic situation complexity become so urgent today? Vessel clearance and channel congestion remain central threats to maritime safety. If we have evaluated traffic complexity accurately and in real time, maritime authorities such as VTS centers can proactively predict risk and optimize allocation of regulatory resource. This is not only essential for ensuring navigational safety, but also mandatory step toward the future development of smart shipping and intelligent maritime systems. Next, I would like to highlight two research gaps identified in current studies. The first is the structural limitation of existing model. Existing traditional models, whether based on rules-based thresholds or statistical methods, suffer from a fatal flaw. They struggle to capture the multi-dimensional and multi-scale non-linear interactions among various indicators. The maritime traffic environment is highly intricate, and its cause relationship are rarely linear. Fixed, rigid rules and statistical approaches are simply inadequate for high-dimensional, nonlinear, and real-time dynamic supervision. Apart from the structural issues of the models, and even more challenge original from the data level. This brings us to second research gap. The servers, the high quality labeled data and process of extreme class imbalance. In reality, maritime traffic remains in low or normal complexity status most of the time. Extreme simple of high complexity are incredible rare. This leads to class imbalance. If we feed such imbalanced data directly into advanced deep learning models, it causes bias or overfitting, destroying predictive accuracy in high-risk scenarios. So, driven by this distinct challenge, we crystallized the exact motivation for why this study must be conducted. Our core driving force stems from these three urgent requirements. First, the maritime community desperately needs technicals that can automatically automatically generate high quality samples. A second, scientific approach is needed to filter out redundancy from complex indicators to build a clean feature space. And finally, we must integrate these elements to establish a future-ready decision support system for intelligent maritime supervision. Okay, let us move to the core part, the methodology framework proposed in this study. Is the following slide where I will explain the detail how we for the data argumentation, future engineering, and ensemble learning together to build this comprehensive supervision model named CGAN and MR XG Boost. Look at this chart, which illustrates the overall workflow of the proposed research. The entire architecture is divided into 3 core steps. Step 1 is data input and indicator extraction. Well, multi-dimensional traffic features are made from raw AS data. Step 2 utilizes the SIGAN to generate and balance high complexity samples. And step 3 implements RMR to select the optimal feature subset, which is then fed into XGBoost for final evaluation. In the feature extraction stage, we first constructed candidate indicators from the traffic demotion. The traffic for demotion primarily reflects the macro level situation of the water arrow. First, the total ship count representing the number of ships in the arrow. The ship density describing the spatial concentration of ships, and finally, looking beyond the present, we calculate the potential inbound flow over 5 minutes, 50 minutes, and 30 minutes horizons to handle the model with proactive predictive capability. Beyond macro quantities, we must also explore the microscopic vessel motion, performance motion. We extract the average ship speed, which defines the general baseline velocity of the water section. More importantly, we calculate the speed variance and hiding variability. Large speed variance implies that fast and slow vessels are heavily interval, while high heading variability indicates numerous vessels are exhausting frequent turning or clearing avoidance maneuvers. These indicators are highly sensitive to complex navigation normal. And the third demotion is also the one that impacts the psychological workload of VTS operators the most, the potential conflict demotion. By computing the relative motion between ship pairs, we derived some critical metrics. These conflict features serve as core metrics for quantifying regulatory pressure. So in summary, we compact the total of 15 initial candidate indicators spanning 3 primary motion, traffic flow, vessel performance, and potential conflicts. All indicators are computed based on 1 minute's analysis time window. This form our initial high dimensional feature space. To address the class imbalance problem caused by the secretary of high complexity samples mentioned earlier, we introduced the conditional GAN, CGAN. Standard GANs can only generate data matching the overall distribution blindly without control over specific categories. The CGAN achieves directional generation by feeding class level as a conditional variable into both the generator and the discriminator. We can supply a high complexity level, forcing it into synthesized high quality, high risk traffic samples that conform to real maritime physical logic, thereby fundamentally solving the data imbalance issue before training. After balancing the data site, the next issue we faced is the feature redundancy. For this, we introduced the RMR algorithm. Culinary often exists among the 15 indicators. For instance, sheep count and sheep density are highly correlated. So such collinearity can cause the typical machine learning model to collapse or become highly unstable. So the RMR algorithm offers an elegant solution. It maximizes the mutual information between features and target class levels, while minimizing the mutual information among the features themselves, selecting an optimal non-repetitive feature subset for the model. Following the data argumentation and the feature filtering, we obtain the ideal input data. The final step is selecting core classifier XGBoost. We selected XGBoost as our primary evaluation engine due to its super performance in tabular data classification. And to validate the utility value of this framework, we conduct an in-depth empirical case study. Next, I will present the specific implementation process and empirical results of our model in the high-density water of the Zhenjiang section of the Yangtze River. The Zhenjiang section is a critical choke point of the Yangtze River. Its complex traffic structure, restricted water, and extreme density make it an ideal yet highly challenging testing ground for maritime complexity evaluation. For more analysis, we further segmented the Zhenjiang section into 3 sub-areas with distinct traffic characteristics. The massive amount of raw maritime data collected cannot be used directly. It must undergo pre-processing. And the pre-processing pipeline involves 3 steps: noise reduction, trajectory interpolation, and segment slicing. A machine learning model requires ground truth for supervised learning. To establish this, we invited a high subsumption expert to manually annotate the data. We invited 15 maritime professionals, including sensor VTS operator, Yangtze River pilots, and captains of ferries who are familiar with these waters. Based on their practical operational experience with safety distance and emergency maneuver and crossing the conflicts, the expert noted each 1 minute's window into 3 distinct complexity level: high complexity, normal complexity, and low complexity. There is a subjective limitation of the expert reliable. We employed a statistical method to perform a scientific consistency test. And this robotically proves that our dataset classification levels possess a solid, objective scientific foundation. To investigate the impact of the data augmentation on model performance, we designed 8 distinct data site configurations. The group of comparative experiments labeled SC1 through SC8 covers rigorous scientific logic. SC1 is a baseline that comparing exclusive real-world role record, and SC2 through SC4 implement targeted augmentation, amplifying the recite high complexity symbol count by 2, 5, and 9 times respectively to observe the effect of mitigating imbalance. SC5 serve as a extreme test containing entirely data generated by CGAN, while C6 through C8 executive global and proportional data site expansion. Through these 8 configurations, we can dissect exactly how CGAN benefits the model. We now enter the quantitative analysis of the experiment results. First, we must verify whether the CGAN achieved stable convergence during its training. The picture illustrates the training trajectory of the CGAN. It's evident that as iterations process, the discriminator's accuracy gradually dropped from its initial absolute dimension and stabilized around 50%. This indicates that the generator has reached a stage where its outputs are indistinguishable from real records. And beyond observing convergence curves, we subjected the generated sample to mathematical statistical testing, and the relative mean error between the generated and the real features remain well below 6%, and all generated items successfully passed the keyest test. Moving to the feature selection stage, the MRMR algorithm eliminated the redundancy and identified the top 9 core features with the highest contribution score. And the features contributing most to maritime traffic complexity are shown in the table. The result aligns closely with intuition of maritime experts. An increasingly crowded space, urgent maneuvers, and a heavy influx of incoming vessels naturally escalated the complex of water section. Now let us examine the direct leap in performance brought by directional mitigating the minority class imbalance. We compared the baseline set SC1 against SC4, which contain a 9-fold directional amplification of high complexity samples. As displayed, the model's macro F1 score directly increased from 0.5138 to 0.5673. Note that macro F1 is a metric highly sensitively to minority class performance. This significant growth directly proves that providing targeted additionals of high-risk minority sample by CGAN can rescue the model's recognition capability in critical river scenarios. And what happened if we do not just replenish the minority class, but globally blend real records with generated data. This brings us to our hybrid advantage configurations as the 8. Compared to the real-only SC1 test, SC1 set and SC8 configuration, which adopts a hybrid global expanded dataset, sees its macro F1 score skyrocket to 0.7044. This result reveals a profound insight. Well, real-world data is authentic. It's more simple size, often limited the true potential of machine learning. Introducing high quality synthetic data, enrich simple generalization diversity while preserving the true physical boundaries. Okay, in conclusion, this study has successfully constructed an intelligent maritime traffic complexity evaluation framework powered by data argumentation, feature refinement, and high performance decision learning. Validate robustly in dense Yangtze River waters. Moving forward, we will continue our research by pushing the algorithm toward all-weather real-time stream data processing, using multi-source environments like weather and tide data, and integrating reinforcement learning to achieve full adaptive intelligent maritime supervision. Okay, that's all my presentations. Thank you very much. Thank you for your time.
Thank you, Dr. Zonki, for your valuable support and collaboration. Is there any question for Dr. Zonki or Toros? Any question? No?
No question. Okay,
Yeah,
thank you.
there's no question. Okay.
Thank you very much.
Thank you very much, Dr. Zonki, again. Now, I would like to express my appreciation once again to all the keynote speakers and participants for their valuable contributions. Moving forward, we will proceed to the next part of the symposium program, which entails scientific studies starting at noon, precisely at 1:30 in Turkish local time. Participants who wish to follow the presentation or present their research in the sessions can access links provided in the symposium program and breakout room as well. Thank you all for your presence and participation in the symposium.